When
Yep.
we talk about artificial intelligence, maybe we'll stay at that topic. I think 2 years ago, there was even 1 or 2 years ago, 2 years ago, you announced something called the estimator, where you said like you take its input parameters, like the degrees of freedom, the physics that's actually running. What the output was, or what you could predict was something like the runtime of the simulation, core hours consumed.
That's right.
When we look at the roadmap, Ian, where does AI or what does AI sit in the future, and how does it augment engineering workflows?
Yeah, it's going to be a really exciting time for engineers because they will be able to leverage AI as AI becomes democratized. And I see cloud engineering simulation as a driver to be able to use more AI in your engineering processes. An example is what I just told you about, how Tesla's using simulated cars driving around in a simulated environment to collect data sets to train their AI. But on a more physical level, we have customers that are using what we call Sim AI today, not to be confused with Sim API, which is our simulation API. But Sim AI is the concept that, let's say you're designing a sensor. Let's say you're Ian Campbell at NextInput, 10 years ago, designing a sensor for a smartphone. And first of all, you've designed your sensor, so you know what the sensor looks like. Then your next goal is to put it into a mechanical assembly. And that mechanical assembly is going to be there's going to be mechanical and manufacturing variants and how that assembly is created, in production. So we have to account for all the different manufacturing variants that is going to affect that sensor. And there's also going to be environmental variants. Once we put the sensor into something like a wearable, it's going to be out in the environment. It's going to heat up. It's going to cool down. It's going to experience shock, vibration, and our sensors have to be robust against that. And our algorithms have to be robust against those different environmental changes, and manufacturing variants. So how do we design these algorithms? Well, one way, and this is what we did at NextInput, we just built a bunch of prototypes and we tested them through rigorous physical testing. We would put systems into environmental test chambers. We'd take them up to 80°C, down to -40°C. We'd inject humidity. We'd put them on shock tables, vibration tables, and get a bunch of data, physical data from the sensors. And then we'd use that data to basically train the algorithms to correct for those different signals so that we could detect the signal that we wanted to detect, which is a human figure on the touch surface. That process that I described for you was, it took us years to do that, to collect that physical data. Now with OnScale, you can just simulate all of those different things happening. You can simulate the manufacturing variants. You can create a million different digital prototypes that reflect the entire distribution of manufacturing variants on a product. You can test all of them, simulate all of them. You can take each one of those and you can put them on a virtual environmental chamber, heat them up, cool them off with thermal analysis. You can put them on a virtual shock or vibration table, subjected to shock and vibration virtually with simulation. And then you can create this massive data set that then you can then use to train your first AI algorithm. And then the moment you make your first prototype, you put that AI algorithm on the first prototype, and guess what? It magically works. And that's an incredible capability that engineers are using OnScale today to train embedded AI using simulated or synthetic data.